the final star will slowly cool and fade away. As it dims, the universe will once again turn into a vast emptiness, devoid of light, life, or meaning. When the last star fades, a very long and dark period will begin, and monstrous black holes will eventually swallow up all matter, only to evaporate into faint glimmers of light. The universe will continue expanding outward until even those faint lights become too scattered, and activity will come to a complete halt. This cold, dark, empty universe might seem like the end of everything we know. However, according to some space experts, the same empty universe in the distant future might trigger a new cosmic explosion, like a fresh Big Bang. Even in this cycle, there's a question about how the first Big Bang could have happened. And with this question, we're left pondering another well-known question. How did something appear out of nothing? To solve these mysteries, we must first gain a clear understanding of the two primary eras of the Big Bang. The first is the Planck epoch, and the second is the Grand Unified Epoch era. Both of these periods occurred just seconds after the Big Bang, during which numerous significant events took place. Nearly 99% of what we observe in the universe today unfolded during those few seconds. In the Grand Unified Epoch era, which was the later stage of the Big Bang, the first matter came into existence. If we want to explain where stable matter, like atoms or molecules, came from, it wasn't present at the Big Bang or for hundreds of thousands of years afterward. We understand how the first atoms formed from simpler particles once conditions cooled down enough, leading to stable complex matter. However, this explanation doesn't tackle the question of something coming from nothing. Now, let's rewind further. The first long-lasting matter particles were protons and neutrons, forming around the 10,000th part of a second after the Big Bang. Before that, there wasn't any material in the usual sense. Physics only allows us to trace the timeline backward to processes predating stable matter. But as of now, physics finds the Grand Unified Epoch too distant to comprehend. This is the time when speculative physics comes in, since we can't generate enough energy in experiments to explore those ancient processes fully. In the early days of the Grand Unified Epoch, the physical world was a mix of short-lived particles, including quarks, which is the stuff making up protons and neutrons. Matter and antimatter played a balancing act, creating and annihilating each other. However, particles don't spontaneously appear. According to quantum field theory, empty space is teeming with energy fluctuations, leading to the emergence and disappearance of particles. It might sound like a math trick, but scientists have actually witnessed these particles in experiments. It's like a hidden dance of tiny building blocks unfolding all around us. But in classical physics, we often think of a vacuum as completely empty, devoid of any matter or energy. Renowned philosopher David Albert critiques explanations that suggest something emerged from nothing during the Big Bang. According to him, the universe always had something in addition to the space-time continuum. Now let's explore where space-time itself came from. Going back to the ancient Planck epoch, which occurred a tiny fraction of a second after the Big Bang. In this era, space and time underwent quantum fluctuations. This era happened even before the Grand Unified Epoch era. Understanding this requires a complete theory of quantum gravity, combining quantum mechanics and general relativity. During the Planck epoch, our usual grasp of space and time falls apart, making our typical ideas about cause and effect unreliable. However, all the theories about quantum gravity suggest there was something real happening during the Planck epoch, some kind of quantum precursor to our regular space and time axis. Simply put, a quantum atom for space and time. The fundamental question persists, and that is, from where did that precursor originate? We still lack a perfect theory of quantum gravity, but ideas like string theory and loop quantum gravity propose that regular space and time emerge, similar to waves on an ocean. Quantum gravity theories propose that at extremely small scales, quantum phenomena influenced the fabric of spacetime as the universe expanded. These quantum fluctuations could have given rise to the macroscopic dimensions of space and the progression of time. According to this hypothesis, the precursor would always exist within the fundamental structure of the universe. It was not born or created just like the energy. Now let's solve the question of how and from where the hot, dense state of the Big Bang came from. Roger Penrose, a Nobel Prize-winning physicist, put forth a fascinating yet controversial model called conformal cyclic cosmology, inspired by a mathematical link between the hot, dense state of the universe at the Big Bang and the cold, expanded state in the far future. Penrose's theory suggests these states become mathematically identical at their extremes. Strangely, a complete absence of matter might give rise to all the matter in our universe. From this viewpoint, the Big Bang seems to emerge from almost nothing. It's what's left when all matter in a universe transforms into black holes, which then become photons and disperse into emptiness. The entire universe originates from something that, looked at differently, is nearly nothing. Understanding how the same state can appear as a cold, empty universe from one angle and a hot, dense universe from another is the challenge. The answer lies in a complex mathematical process known as conformal rescaling. This geometric transformation alters the size of an object while preserving its shape. It's like resizing a picture on a computer. The proportions and angles of the image remain the same, but the overall size is adjusted. Similarly, in conformal rescaling, the geometry of an object is transformed in a way that doesn't distort its fundamental structure. Penrose showed that the cold, dense state and the hot, dense state can be connected through conformal rescaling, aligning their space-time shapes, though not their sizes. Understanding how two objects with different sizes can be identical is tricky, but Penrose argues that size doesn't matter in extreme situations. In conformal cyclic cosmology, the explanation shifts from old and cold to young and hot. The hot, dense state exists because of the cold, empty state, but it's not the typical cause and effect relationship with respect to time. In these extreme states, both size and time don't matter much. The cold, dense state and the hot, dense state essentially exist on different timelines. The cold, empty state would continue indefinitely in its own time, while the hot, dense state it leads to is on a new timeline. To understand the hot, dense state emerging from the cold, empty state, consider it more as a non-causal process. Philosophers of science, particularly those in the field of quantum gravity, delve into concepts where conventional cause and effect principles appear to fall. As we explore the unknown, separating physics from philosophy becomes challenging. Conformal cyclic cosmology gives us speculative answers about the origin of our Big Bang. However, even if Penrose's ideas are proven right in future cosmological discoveries, a deeper philosophical question remains. Where did physical reality itself originate? How did the entire system of cycles come into existence? Our focus here centers on explanations within the realm of physics, offering three main possibilities for the deeper question of how cycles began. One option is that there's no physical explanation at all. Another suggests endlessly repeating cycles, with each cycle's initial quantum state explained by the previous universe. The third proposes a single cycle and a repeating universe, where the cycle start is explained by its own end, avoiding uncaused events. In simpler words, the second possibility implies a new cycle each time, somehow connected to the past cycle. The third suggests that each new cycle is an exact reflection of the previous one, originating directly from it. Penrose favors the second theory. In his view, each cycle involves random quantum events leading to differences between cycles. This idea could help experimental physicists observe traces of the old universe in the radiation from the Big Bang, as seen by the Planck satellite. Penrose's team claims to have found such traces, but the observations are contested. While endless cycles are crucial to Penrose's vision, conformal cyclic cosmology can shift to a one-cycle form. In this case, physical reality involves a single cycle from the Big Bang to a maximally empty state and back again, giving rise to the same universe repeatedly. This aligns with the many worlds interpretation of quantum mechanics, stating that every measurement outcome occurs in a separate universe within a multiverse. Therefore, in a quantum parallel world, an event occurs even if it has a low probability. Simply put, understanding what happened before the Big Bang is complex. However, according to Penrose's hypothesis, which is currently favored, the universe goes through a continuous cycle from the Big Bang to a maximally empty state and then starts anew with another Big Bang. Each cycle creates a universe similar to the previous one, forming a repeating and endless cosmic sequence. So, before the Big Bang, a universe contracts, its energy is consumed by black holes, and then a new Big Bang occurs, giving rise to a new universe. That is the answer we are looking in the video. Indeed, this is the solution to the big question, and I'm confident that we'll figure out this puzzle in the future. Until then, let's keep exploring such fascinating and complex topics. See you in the next video.